Welcome to this comprehensive tutorial on FlexAttention, a groundbreaking feature from Pytorch that brings together the flexibility of Pytorch with the performance of FlashAttention. This notebook builds upon the original work by Team Pytorch, specifically Driss Gessis, Yanbo Liang, Joy Dong, and Horace He, enhanced with additional visualizations, comprehensive explanations, and extended analysis to deepen our understanding of the concepts. In this tutorial, you'll learn to master FlexAttention's powerful capabilities. We'll explore how to implement various attention variants using the ScoreMod API, work with BlockMask for efficient sparse patterns, and combine multiple attention mechanisms for complex use cases. You'll also discover practical optimization techniques for production deployment, including caching strategies and memory considerations. By the end, you'll have both the theoretical understanding and practical skills to leverage FlexAttention in your own projects. Now let's dive into the background and understand why FlexAttention is such an important development. In theory, attention is all you need, which is the famous paper title that introduced the transformer architecture. However, in practice, we also need highly optimized attention implementations like FlashAttention to make these models efficient. The challenge is that while fused attention implementations have dramatically improved performance and enabled long contexts, this efficiency has come at a significant cost: the loss of flexibility. You can no longer try out a new attention variant by simply writing a few Pytorch operators. Instead, you often need to write a completely new custom kernel. This creates what we call a software lottery for attention variants. Researchers want to use various attention patterns like causal attention, relative positional embeddings, ALiBi, which stands for attention with linear biases, sliding window attention, PrefixLM, document masking, sample packing, tan soft capping, and paged attention. Even worse, folks often want combinations of these patterns. Let me show you a comparison image that illustrates the problem and solution. Let's set up our environment and import all the necessary libraries. We'll import Torch for our core tensor operations, torch.nn.functional for various neural network functions, and specifically the flex_attention module along with create_block_mask, and _masks, and/or _masks from torch.nn.attention.flex_attention. We'll also import NumPy and Matplotlib for visualization, and suppress warnings for cleaner output. Great, we're using a CUDA device, which means we have an NVIDIA GPU available for acceleration. This will help us see the full performance benefits of FlexAttention. Now let's understand the core concepts of how attention works. The classic attention equation is attention of Q, K, V equals softmax of QK transpose divided by square root of D_K, all multiplied by V here. Q is the query matrix, K is the key matrix, V is the value matrix, and D_K is the dimension of the keys. Let me show you the standard scaled dot product attention implementation in code. Here's our vanilla attention implementation. This function takes Q, K, and V tensors with shape batch_size, num_heads, sequence_length, head_dim. First, we compute attention scores by multiplying Q with K transpose and scaling by the square root of head dimension. Then we apply softmax to get attention weights, and finally multiply by V to get our output. Let me run this with some test tensors. Perfect, our vanilla attention is working correctly, producing output with shape 2, 4, 128, 64, matching our input dimensions. Now let's explore FlexAttention and how it adds flexibility through the score_mod function. The key innovation is that FlexAttention allows you to modify attention scores with a user-defined function. The equation becomes FlexAttention of Q, K, V equals softmax of score_mod applied to QK transpose divided by square root of D_K. All multiplied by V, the score_mod function receives the score, which is the dot product of a query and key token, the batch index B, head index H, query position Q_IX, and key value position KV_IX. Now we'll explore various attention variants using FlexAttention's score_mod API. Let's start with different examples to see the flexibility this provides. Let's start with full attention, which is essentially a no-op where we just return the score unchanged. This demonstrates that FlexAttention can reproduce standard attention perfectly. We'll compile flex_attention for better performance and define a NUP function that just returns the score unchanged. Let's test this and verify it matches vanilla attention. Excellent, FlexAttention with a no-op score modifier produces output with the same shape. And the maximum difference from Pytorch's built-in scaled.product attention is only 0.000002, showing nearly perfect numerical agreement. Next, let's implement relative position encodings, which adjust attention scores based on the distance between query and key positions. This is useful for models that need to understand relative positioning of tokens. Here's our relative positional encoding function that adds a bias based on the difference between query and key positions. Let me test this and visualize the relative position bias pattern. The output shape is correct, and the visualization shows the relative position bias pattern. Notice how the bias forms a diagonal gradient, with positive values above the diagonal where queries attend to earlier keys and negative values below where queries attend to later keys. Now let's implement ALiBi, which stands for attention with linear biases. This is shown in the image as a technique that applies head-specific linear biases based on position distance. It's used in models to help with length generalization. Let me generate ALiBi bias slopes for each attention head. ALiBi uses a geometric sequence of slopes that are different for each head. Then we'll create an ALiBi function that applies these slopes based on the distance between positions. We can see the ALiBi slopes for our 4 heads, ranging from 0.25 to 0.0625. The visualization shows how each head has a different bias pattern, with steeper slopes for some heads and gentler slopes for others. This diversity helps the model attend to different ranges of context. Next, let's implement soft capping, which prevents attention logits from growing too large. This technique is used in models like Gemma 2 and Grok 1 to improve training stability. Here's our soft cap function with a cap value of 20. We divide the score by the soft cap value, apply tan, then multiply back by soft cap. This creates a smooth capping effect. Let me test this and visualize how it affects the scores. The soft capping output shape is correct. The visualization clearly shows how soft capping smoothly limits scores to the range between -20 and +20, preventing extreme values while maintaining differentiability. Unlike hard clipping, this provides a smooth transition that's better for gradient flow. Now let's implement causal masking, which is fundamental for autoregressive models. Causal attention ensures each token can only attend to previous tokens and itself, not future tokens. Here's our causal mask function that returns the score if the query position is greater than or equal to the key position, otherwise returns -infinity to completely mask out that attention. Let me test this and visualize the pattern. Perfect, the causal mask is working correctly. The visualization shows the lower triangular pattern where each position can only attend to itself and previous positions. The check marks indicate where attention is allowed. Now let's make causal attention more efficient using BlockMask. Instead of applying the mask in score_mod, we can use a mask_mod function that returns true or false to indicate whether a position should be computed at all. This allows FlexAttention to skip unnecessary computations entirely. Excellent, causal attention with BlockMask produces the same output shape but achieves approximately 50% sparsity. This means we're only computing about half the attention scores, making it much more efficient. Let's look at sliding window attention combined with causal masking. This pattern, used by models like Mistral, limits attention to only recent tokens within a window. The image shows how this creates a band diagonal pattern. Here we combine sliding window with causal mask. Each position can only attend to positions within a window of 32 tokens behind it. Let me create the BlockMask and visualize this pattern. The sliding window causal attention is working perfectly. The visualization shows a band diagonal pattern where each position attends only to a limited window of previous positions, reducing computational complexity while maintaining local context. Now let's implement PrefixLM Attention. As shown in the image, this pattern performs bidirectional attention on a prefix portion of the sequence and causal attention on the rest. This is useful for models that have a prompt or context that should be fully visible, followed by generation that should be causal. We'll define different prefix lengths for each batch element, then combine prefix and causal masks using or underscore masks. This allows bidirectional attention within the prefix and causal attention afterward. The PrefixLM pattern is working correctly with different prefix lengths per batch, 32 and 48. The visualization shows the characteristic pattern where the prefix region has full bidirectional attention, shown by the filled rectangle on the left, while the rest follows causal attention. Let's implement document masking, also known as handling jagged sequences. As shown in the image, this allows us to pack multiple sequences of different lengths into a single tensor while ensuring they don't attend to each other. This is crucial for efficient batching. We'll create document IDs for packed sequences. In this example, we have 3 documents with lengths 30, 40, and 58 tokens. The document masking function ensures attention only happens within the same document. Document masking is working perfectly. We have 3 documents packed together, and the visualization shows the block diagonal pattern where each document only attends to itself. The red dashed lines indicate document boundaries. Now let's explore advanced compositions. The image shows how we can combine multiple masks for complex attention patterns. Let's create document-wise causal attention, where we have both document boundaries and causal masking within each document. Here we combine document masking with causal attention. Each token can only attend to earlier tokens within its own document. This is useful for training on multiple sequences simultaneously while maintaining causality. The document-wise causal attention is working correctly. The visualization shows block-lower triangular patterns where each document has its own causal mask. This allows efficient training on multiple sequences without cross-contamination. Let's discuss performance. The image shows performance comparisons, and FlexAttention achieves excellent results across different attention patterns while maintaining the flexibility to implement new ones. FlexAttention also maintains excellent numerical accuracy compared to standard implementations. The image shows the RMSE distribution comparing FlexAttention to standard implementations. Let's test the numerical accuracy of FlexAttention by comparing it against Pytorch's built-in scaled dot product attention. We'll run multiple samples and calculate the root mean square error. Excellent numerical accuracy. The mean RMSE is extremely low at around 0.000002, with very low standard deviation and maximum error. The histogram shows that FlexAttention maintains consistently high accuracy across all samples, making it suitable for production use. Let's understand BlockMask Internals. As shown in the image, BlockMask optimizes sparse attention by categorizing blocks into 3 types. Full blocks where all elements are computed with no masking overhead, partial blocks where some elements are masked requiring masking operations, and empty blocks that are skipped entirely for maximum efficiency. Now let's cover some frequently asked questions and best practices. An important question is, when does FlexAttention need to recompile? FlexAttention leverages torch.compile and smartly avoids recompilation when tensor values change, including captured tensors, or when block sparsity patterns change, which only needs BlockMask recomputation. However, it does recompile when the score_mod or mask_mod function logic changes, or when tensor shapes change significantly. Let me demonstrate that changing bias values doesn't require recompilation. We'll create a bias modifier function and test it with different bias values. Perfect, we can see that both outputs have the correct shape and no recompilation was needed when we changed the bias values. This is because FlexAttention is smart about when recompilation is necessary. Let's discuss best practices for BlockMask. First, cache block masks when possible since computing them is expensive. Second, broadcast over batch and heads using B equals none and H equals none when the mask is the same across batch and heads. Third, compile create underscore block underscore mask with underscore compile equals true for better performance. And fourth, for simple patterns, consider writing custom BlockMask constructors. Here's an example of efficient BlockMask caching using Python's functools.lru_cache. We cache block masks for different sequence lengths so they can be reused. Great, block masks are now cached for efficient reuse. The cache info shows we had 1 hit when we requested the 128 length mask again, and 2 misses for the new masks. This caching strategy significantly improves performance when using the same mask patterns repeatedly. Let's discuss memory considerations. BlockMask metadata size is batch underscore size times num underscore heads times q underscore len divided by block underscore size times kv underscore len divided by block underscore size. The default block size is 128. For a 1 million token sequence, this results in about 60 megabytes of metadata. You can increase the block size to reduce memory usage. Let me calculate BlockMask memory usage for different configurations. We'll look at various sequence lengths and block sizes to understand the memory trade-offs. The table shows memory usage for different configurations. Notice how a sequence length of 131,072 tokens with the default block size of 128 uses about 128 megabytes, but increasing the block size to 512 reduces this to just 8 megabytes. However, larger block sizes may reduce efficiency since they create coarser-grained sparsity patterns. Let's wrap up with the conclusion. FlexAttention provides 5 key benefits. First, flexibility to implement any attention variant with simple Python functions. Second, performance through automatically generated fused kernels competitive with handwritten ones. Third, ease of use with no need to write custom CUDA or Triton kernels. Fourth, composability to combine multiple attention patterns easily. And fifth, automatic gradients where the backwards pass is generated automatically. The key takeaways are to use score_mod for general score modifications, use mask_mod with BlockMask for sparse patterns, cache block masks when possible, compile with torch.compile for best performance, and combine masks with and underscore masks and/or underscore masks. For further resources, check out Attention Gym on GitHub for more FlexAttention examples, the Pytorch documentation for official API docs, and the original blog post. With FlexAttention, trying new attention variants is only limited by your imagination. That's all for this comprehensive FlexAttention tutorial. Thank you for following along, and I hope you're excited to try FlexAttention in your own projects.